Here are solutions to homework set number 9 for ECE 461-6661 control systems. This homework set looks at feedback control using PID, compensators, and meeting design specs. Delays will actually be next week. The first problem is given a fourth order system. Okay, what this corresponds to is a 10-stage RC filter, heat equation. I just took the 4 dominant poles, call that my model. Come up with a feedback compensator to give me 20% overshoot. And we'll look at I, PI, kind of a PID compensator. So the first problem is an I compensator. Here's your G of S. What an I compensator means is that add an integrator and a gain K. What the integrator does, that makes this a type 1 system, so there's no error for step input. To find K, what I want to do is sketch the root locus of the open loop system. Well, root locus of the closed loop system. Multiply G and K together, I get G times K, same system with an integrator. Sketch the root locus. In MATLAB I can do that. I'll just input G times K. I've got no zeros, poles at 0, minus 0.47, yada yada yada. K is, I'm going to guess, what is the answer? I think the answer is somewhere between 0.01 and 100 with 1,000 points. Draw the root locus for that system. Now with MATLAB, it doesn't draw the damping lines. For 20% overshoot, what that means is 20% overshoot tells you that the damping ratio of zeta is 0.4559. You can go to the second order damping curves. It's between 0.4 and 0.5, about 0.45. That means the angle 63 degrees. And the tangent of the angle is 1.95, basically 2. So to draw the damping line, I'm going to freeze the root locus plot and then draw the red line. It's going to go from the origin, 0, 0, and the left side, I just guessed, minus 3 per x, up 1.95 times 3. So it's over 1, up 2, over 1, up 2. That draws the damping line. That draws the root locus. I then zoomed in to get this part of the curve. What I'm looking for is this point. Zoom in on that, and I can find that point is roughly minus 0.188 plus j 0.368. Once I find S, that point right there, any point on the root locus, g times k is minus 1. So evaluate g times k at that point, I get almost a negative real number. This should be 0. It's not, saying this point is a little bit off. It's close, but a little bit off the root locus. So almost on the root locus. Pick k to make the gain 1. So pick k to be 1 over the absolute value of this. K is 0.5337. So that's k. The closed loop system is g times k, adjusted with k, over 1 plus g times k. Find the closed loop poles, and there's one pole right where I put it. This pole actually is on the root locus. Its complex conjugate, and 3 others. It's a fifth order system. I've got 5 poles. I placed one of them. The other 4 go somewhere. Once I've got the closed loop system, I know how it's going to behave. 4 over the real part is your settling time. I've got 20% overshoot, so the step response will look like this. Type 1 system, it goes to 1, guaranteed. Here's 20% overshoot. And the settling time is about 21 seconds. To check it, I could throw it in MATLAB, Simulink, Circuit Lab. I'm going to use Circuit Lab. I kind of like Circuit Lab. Here's G of S. Here's my compensator, K of S. Close the feedback loop, take the step response. And sure enough, 20% overshoot, no error for step input. Settling time is about 21 seconds. Just like I expected. Actually, the overshoot is a little bit less than 20%. The reason being is the dominant pole would give you 20% overshoot if it was a second order system. This is actually a fifth order system. The other 3 poles smooth out the step response and bring it a little bit less than 20%. That's inherent with root locus. Root locus is inherently a little bit conservative. Close, but a little bit off. if I want to build that circuit, I want to build this integrator. Here's an integrator circuit, 2 degrees of freedom, 1 constraint, pick one. But let C be 1 microfarad, then 1 over RC is 0.5377. Solve for R, I get 1.89 meg. One of many solutions. Problem 2. Okay, suppose I'm willing to splurge. Come up with a PI compensator. Now, PI compensators cost an extra 2 cents to build, basically add a resistor. What they do in terms of root locus is that lets you add a 0. So if I can put the 0 anywhere I want, where I put it is cancel the slowest pole. Now back with the lead compensator, I'd keep this pole, cancel the next slowest one, because I like type 1 systems. That's the closest I get with the lead compensator. With the PI, what I'm going to do is take this pole at 0.47 and move it to the origin. So in terms of root locus, there was a pole right here. I'm going to get rid of it, move it to the origin. That makes it a type 1 system. Now there's no error per step input. So here's G of S, here's K of S. Multiply the two together. That 0 cancels with that pole, gives you G times K. Now let's sketch the root locus of G times K, and you get this from MATLAB. Freeze the root locus plot, add the damping line in red, and here's the point I'm looking for. Where does the root locus intersect my damping line? Zooming in on that, that point is roughly -1 plus J2. Evaluate that. G times K at that point is negative real. That's good. That says this point's on the root locus. At any point in the root locus, G times K is -1. There's the minus sign, but the gain's wrong. Pick K to make the gain 1, and that gives you K of S. When I form the closed loop system, GK over 1 plus GK, I have a pole right where I put it, -1 plus J2, plus 3 other poles. There's actually a fourth pole at -0.47, but there's a 0 sitting right on top of it. The settling time is for the real part of the pole, 3.8 seconds. That's the advantage of the PI. I went from 21 seconds settling time with an I compensator to 3.8 seconds for PI. And no error per step input. So the step response should look like this. Same as before, 20% overshoot. DC gains 1, type 1 system, but now the settling time should be 3.8 seconds. Checking. Check in MATLAB, Simulink, Circuit Lab, pick your favorite. I'm going to use Circuit Lab again. Here's G of S, no change. K of S, I now make that a PI compensator. Take the step response, and sure enough, 20% overshoot, a little bit less, but pretty darn close. No error per step input, and a settling time of about 4 seconds. To come up with a circuit to implement that, here's my K of S. Here's my PI compensator. I've got 3 degrees of freedom, 2 constraints, so somebody's arbitrary. But let this be 1 meg. As S goes to infinity, this is gone. S goes to infinity, this is 5.4. So this is 1 meg over 5.4, 182K. The 0 is right here. At DC, this is a capacitor. At high frequencies, it's a 1 meg. They switch at 1 over RC. They switch at 0.47 radians per second. So pick C, so that 1 over RC is 0.47. You wind up with C is 2.12 microfarads. Okay, problem 3. Suppose I want to come up with any old compensator I want. Lead, PI, I don't care. Add poles, add zeros, do whatever it takes to meet these specs. I want no error per step input, 2% settling time at 2 seconds, and 20% overshoot. Translating, that says make this type 1 system, so I know right away that K of S has to have a pole at S equals 0, because there currently isn't one. I want to place the closed loop pole at -2 for the settling time, plus J4 for a 20% overshoot. So in the root locus, here's my target. make it a type 1 system, and put the dominant pole at -2 plus J4. So what I do in that case is I have a pole at 0.47, 3.4, 9, and 16. I want to put the dominant pole at -2 plus J4. So what I'm going to do is add a pole at s equals 0, type 1. These come together, split apart, and too slow. So get rid of the pole at 0.47. Now these two, pole at 0 and 3.4, come together, and again too slow. So get rid of the pole at 3.4 by putting 0 right on top of it. Now these come together, split apart, and are too fast. That's good. So this is good enough, but I want to have a finite gain as s goes to infinity. So add a pole somewhere. Slide that pole around. As I slide it in, I'm going to push the root locus right, push it so it passes through this point. So that's the approach. I'll first pick the form of k of s. Add a pole at s equals 0. Start canceling poles. You could cancel more if you want. This is sufficient. Cancel poles until I'm too fast. Add a second pole, slide it around till the angles add up. So there's the form of k of s. Here's g times k. I know that at -2 plus J4, all the angles add up to 180 degrees. That's conditioned for root locus plots. Analyze what I know. I don't know k, I don't know a. What I know adds up to -161 degrees. I'm off by 18 degrees. So what I want is at this point, -2 plus J4. Here's my point A. This angle right here is 18 degrees. So doing some trig, this side is 4, this side is 4 over tangent of 18 degrees plus 2. A is 13.9. Here's the form of k of s. Analyze what I know. G times k at my design point. Angles add up to 180. That's good. That means this point was correct. K is wrong. Pick k to make the gain 1. So voila, there's k of s. As a check, given that k of s, plot the step response of the closed loop system, and I've got 20% overshoot, no error per step input, and a settling time of 2 seconds. A circuit to implement it is, I don't know what this circuit is, so split it up. I'll split it up as a lead compensator and a PI. The lead compensator is here. Here's the PI compensator. Lead compensator, 4 degrees of freedom, 3 constraints. Let this be 1 meg. S goes to infinity, the gain is 8. S goes to infinity, this is a short. That's 1/8 of 1 meg, 122K. S goes to 0, the gain is 8 times 3 over 13. Total resistance is 500K, that's 122. Here's the remainder. 1 over RC is 3. The PI compensator, 2 constraints, 3 degrees of freedom. Let this be 1 meg. S goes to infinity, the gain is 5. 1 over RC is 0.47. Finally, if there's a delay in the system, same procedure. I pick the form of k of s, take g times k, analyze at my design point, and I got a problem. My phase is too much. I need to have a negative angle for my pole A. If I'm past 180, what that's telling me is I haven't added enough zeros. I need to add another 0. So add another 0. Now, analyze at my design point. I'm at 154 degrees. I'm off by 25 degrees. So the 2 poles that I added 3 zeros, meaning add 3 poles. These 2 poles have to contribute 25 degrees. Put them in the same spot means that each pole contributes 12 degrees. Doing some trig, A is at 19.77. So here's G times K. At my design point, angles add up to 180. It does. That's good. That tells me that this number right here is correct. to make the gain match up, pick K to make the gain 1. K is 109. So here's K of S. Checking the design in Circuit Lab, here's K of S. Circuit Lab doesn't do delays, so here's a second order Pate approximation for a 0.1 second delay. Here's G of S. Take the step response, 20% overshoot, 2 second settling time, no error per step input. That works. So that was homework set number 9 for 461-661 controls.